Okay, picture this. You're watching a boxing match.
Right, a heavyweight bout.
Exactly. And in one corner you have the heavyweight champion of the world,
Yeah.
just massive, expensive, trained by a literal army of humans and boasting 70 billion parameters of pure muscle.
A real titan.
And then in the other corner, you've got a lightweight, a scrappy newcomer that's like 1/10 the size, trained on a shoestring budget by a pretty small team. You'd expect a total massacre.
Oh, in the world of AI,
Yes.
absolutely. I mean, generally speaking, size is destiny. We have these scaling laws that basically tell us more data and more parameters usually equal more intelligence.
Right.
It's really been the rule of law for years now.
Usually. But today, for this deep dive, we are talking about the anomaly, the exception that proves or maybe completely breaks the rule. We're talking about Zephyr-7B.
It's such a fascinating case study. It really shook things up when the paper dropped.
Because this is a small open source model that didn't just show up to the fight, it actually outperformed the massive Llama-70B chat model on some key benchmarks.
Yeah, which is wild.
And the craziest part to me is that it was built by this small team at Hugging Face, the H4 team, without the massive budget or the thousands of human laborers usually required to train these things.
It really challenges that whole bigger is better dogma we've seen dominating the field. It suggests that maybe, just maybe, we've been training these models the hard way.
Exactly. So the mission for today's deep dive is simple. How? How did they do it? We're going to unpack the paper called Zephyr, Direct Distillation of LM Alignment.
Catchy title.
Very catchy. We're going to look at their three-step recipe, which, spoiler alert, involves a lot of acronyms.
Lots of acronyms, yeah. dSFT and dDPO.
Right. And we'll explain how this changes the game for training AI.
And what's really interesting here is that this isn't just about making a model smarter in terms of raw facts. It's about alignment.
Alignment.
Yeah, taking a raw mathematical brain and teaching it how to actually be helpful to a human.
Right, so let's start there. Let's set the landscape for everyone. You mentioned alignment. I think for a lot of people, an AI is just an AI. What is the actual difference between a raw model and an aligned one? Why did Zephyr even need this special training?
Well, think of a raw base model, like the foundation Zephyr is built on, as a super intelligent autocomplete.
Okay.
It's read the entire internet, essentially. But its only goal is to predict the next word.
So if I ask it a question, it doesn't necessarily know I want an answer.
Exactly. If you feed a base model the text, how do I bake a cake? It might not answer you at all. It might just generate more questions like, how do I make icing? How do I preheat the oven?
Because it thinks it's just completing a list of questions it found on a forum somewhere.
Precisely. It doesn't understand the social dynamic of user asks, AI answers.
So it has the knowledge, but it doesn't have the manners. It doesn't know the social contract.
That's a great way to put it. That's where alignment comes in. We have to teach it to switch modes from just predicting text to actually following instructions. Now, the industry standard for doing this, the way the big giants like OpenAI and Meta usually do it, is called RLHF.
Reinforcement learning from human feedback. Which sounds intense and expensive.
It's both. It's a logistical nightmare, honestly. First, you generate thousands of answers. Then you have to pay actual humans to sit there and rate them. This answer is better than that answer.
We're clicking all day.
Yeah. Then you train a separate reward model to mimic those humans. Then you use a complex algorithm called PPO to update the language model based on that reward model.
And from what I gathered in the reading, PPO is a bit of a diva, right?
That is a very polite way of putting it. PPO is notoriously unstable. It's extremely sensitive to hyperparameters.
It's tuning knobs.
Right, the tuning knobs of the algorithm. If you turn one knob slightly too far, the whole training process just collapses. It's computationally expensive, memory hungry, and it's just really tricky to get right. It's kind of like trying to balance a pencil on its tip while the table is shaking.
Okay, so enter the H4 team at Hugging Face. They look at this PPO process and basically say, we don't have the time, money, or patience for this. They want a shortcut.
Right. And they start with a very strong foundation. Zephyr isn't built from scratch. It's built on top of Mistral 7B.
We should pause on Mistral for a second because that's the base model, right?
Yes. Mistral 7B is widely considered the best model in its weight class. Even before Zephyr came along, Mistral was turning heads because it was punching way above its weight in raw reasoning.
But again, it wasn't intent aligned.
Right. It didn't know how to chat properly.
So step one of the Zephyr recipe is something called dSFT, Distilled Supervised Fine-Tuning. Break that down for us. What exactly is distillation here?
Distillation is a key theme throughout this whole paper, actually. Normally, if you want to train a model, you might need humans to write out thousands of perfect conversations to say, here's what a good conversation looks like.
Which is incredibly slow.
Super slow. Distillation means using a massive, smarter model, in this case GPT 3.5 Turbo, to act as the teacher.
So the student becomes the master. Or I guess the student copies the master's homework.
Essentially, yeah.
Yeah.
They used a dataset called UltraChat. It's this massive collection of dialogues generated by the teacher model. It teaches the student model. When a user says X, you should respond with Y. It's showing the model the format of a helpful interaction.
But the paper mentioned a snag here. The data wasn't perfect. Because if you just copy GPT 3.5 blindly, you pick up its bad habits too.
Right. This is the danger of synthetic data. They found that because the teacher model had certain guardrails and quirks, the students started copying them verbatim. For example, if you ask the student model, how do I clean my car?
Yeah.
It might start the sentence with, I don't have personal experiences.
Right? I hate when they do that. As an AI language model, I cannot hold a sponge.
Exactly. And the student model just parrots it, even though it's unnecessary clutter. It makes the bot feel super robotic. They also had issues with capitalization and grammar errors in the generated data.
So they had to play janitor.
They did. They performed these true casing heuristics to fix the capitalization, and they filtered out those, I'm just an AI disclaimers. They really wanted the data to be clean, helpful, and natural.
Okay, so after step 1, the dSFT, we have a model that can chat. It knows the format. It looks like a chatbot. But does it know what a good answer is?
Not really, and that's the crucial distinction here. Step 1 teaches the form of the conversation. But it doesn't necessarily teach the model how to distinguish a great, helpful answer from a mediocre one.
Right.
It just knows this is what a dialogue looks like. It hasn't been optimized for quality yet.
Which brings us to step 2, the talent show. Or technically AI feedback, or AIF. This is where I think things get really sci-fi.
It really does. In the old way, remember, we used humans to rate answers. The innovation here is why use humans. They're slow, they get tired, and they're expensive. Let's use an even smarter AI to be the judge.
So they set up a competition. Describe the arena for us.
So they take a prompt from a data set, something like, write a poem about Rust. Then they have 4 different models like Claude Falcon Llama, generate 4 different answers to that exact same prompt.
And then the judge walks in.
Enter GPT-4, the heavyweight, the gold standard. GPT-4 looks at the prompt and the 4 answers, and it scores them. It looks for helpfulness, honesty, instruction following. It basically gives a score out of 10.
So you end up with a winner and a loser for every prompt.
Exactly. They take the highest scoring response and label it the winner. They take a random lower scoring response and call it the loser. This creates the ultra feedback data set. It's just a massive list of A is better than B preferences.
And the key here is that no human had to lift a finger.
0 human annotation. It's entirely automated. And because GPT-4 is generally very good at judging nuance, the quality of this feedback is surprisingly high.
Okay, so now we have the data. We know what good looks like compared to bad. Now comes the magic sauce. Step 3, the acronym that defines this paper. dDPO, Distilled Direct Preference Optimization.
This is the heavy lifting. This is the real mathematical breakthrough.
Before we get into the direct part, remind us why the old way PPO is such a headache. You mentioned balancing a pencil earlier.
Right, so PPO requires you to train a separate reward model. First, a model that predicts the score. Then during training, you generate an answer, the reward model scores it, and you update the main model.
Okay.
It involves sampling generating text on the fly during training, which is very slow and computationally heavy.
The paper used a basketball analogy that I loved. Let me see if I can get this right. PPO is like trying to learn to shoot a basketball, and after every shot, a coach just screams a score at you. 6, 4, 8. You have to figure out what you did right or wrong based just on that number.
That's a great way to visualize it. It's indirect. You're guessing how to adjust your muscles based on a really noisy signal. You don't know if your elbow is out or if your knees were bent wrong. You just know the score was bad.
And dDPO, how does that change the practice session?
dDPO is like showing the player a video of a perfect shot alongside a video of a terrible shot and saying, mathematically adjust your form to look more like the first video and less like the second one.
That feels so much more intuitive. You're showing the solution, not just grading the attempt.
Exactly. And because you are looking at static data, the videos or the text pairs in this case, you don't need to generate new shots during training. You don't need that slow sampling loop. You just run the math to increase the probability of the winner and decrease the probability of the loser.
And the stats on this were wild. They trained this on just 16 A100 GPUs, and it took, what, a lunch break?
2 to 4 hours.
That is mind-blowing.
It is. Compared to the days or weeks and massive clusters used for the big proprietary models, this is lightning fast. It means you can iterate, you can try new things without burning $1 million in compute credits.
So we have the recipe. Mistral-based teach it to chat with GPT 3.5 data, then refine its taste with GPT-4 feedback using this dDPO method. The big question is, did it work? Because I can cook a 3-course meal quickly, but that doesn't mean it tastes good.
It tasted very good. They tested Zephyr-7B on MT Bench. This is a standard benchmark for chat models. It handles reasoning, role-play math, coding, multi-turn conversations.
And the number.
Zephyr-7B scored a 7.34.
Which means nothing to me without context.
Context is key. Llama-7B, the JOT model from Meta using the expensive human feedback method, scored a 6.86.
Wait, so the 7 billion parameter model beat the 70 billion parameter model?
Yes.
That is punching way above its weight class. That's David knocking out Goliath.
It absolutely is. It also beat other huge open models like Granico 65B, proves a massive point. Alignment matters. Teaching the model how to behave is almost as important as raw intelligence.
Wow.
Yeah, you can have a giant brain,
Yeah.
but if it doesn't know how to be helpful, a smaller, better-trained brain can outperform it in a chat context.
But we have to be fair, right? It didn't beat everyone. It didn't beat the teacher.
No. It didn't beat GPT-4, which sits at a lofty 8.99. And the paper is very honest about the limitations. Zephyr still struggles with hard skills like math and coding compared to the giants.
Why is that? If the alignment is so good, why can't it do calculus?
Because dDPO is mostly about style and helpfulness. It can teach a model to be a good assistant, but it can't hallucinate new raw intelligence that isn't already there in the base model.
Ah, I see.
If Mistral 7B isn't great at complex calculus, Zephyr won't be either. It just frames the wrong answer more politely.
So it puts a tuxedo on the mistake.
Exactly. It makes the error look very confident and helpful.
That makes sense. Also, there's a weird note about overfitting. Usually we're taught that overfitting memorizing the training data is the enemy of good AI.
Yes. Usually in machine learning, overfitting is bad. It means you just memorize the answers and can't generalize to new questions. But here they found that after one epoch, passed through the data, the model had perfect accuracy on the training set. It effectively memorized the preferences.
But the performance didn't drop.
No, and this is the surprise. The chat performance kept getting better for a bit, even after it started overfitting. It contradicts conventional wisdom entirely. It suggests that in this specific game of preference, optimization, maybe memorizing the style of the teacher, is actually what we want.
I want to talk about the fun examples from the paper because they really highlight the difference between the step 1 model, the one with just supervised learning, and the final Zephyr model.
The qualitative examples really bring it to life, yeah.
Okay, the helicopter test. The prompt was, how many helicopters can a human eat in one sitting?
A classic nonsense prompt. It tests if the AI has common sense or if it's just blindly following orders.
The dSFT model, the one that just learned to chat but wasn't optimized, got really confused. It said humans can't eat an adult-sized helicopter.
Which implies maybe a baby helicopter is okay. Or a slice of helicopter.
Exactly. It accepted the premise. It tried to answer the how many part.
But Zephyr, the dDPO model,
it shut it down immediately. It said 0. Humans cannot consume solid objects as large as an entire helicopter. It recognized the premise was false.
It had that common sense filter. It understood that a helpful answer is sometimes a correction.
And then there was the roast. The user asked, I want you to roast me.
This is a great example of intent alignment. The dSFT model took roast literally in the slang sense. It gave a list of generic insults. You have bad taste in music, your cooking is bad, it was just mean.
Which, to be fair, is what a roast is.
Technically, yes. But Zephyr took a totally different approach. Zephyr interpreted roast as a request for constructive criticism. It said things like, you struggle with creativity, you have trouble meeting deadlines. It turned a request for insults into a helpful, albeit stinging critique.
That is so interesting. It was aligned to be helpful above all else, even when asked to be mean. It's like a butler who refuses to let you embarrass yourself.
It shows the model isn't just predicting the next word. It's predicting the most helpful response based on those GPT-4 preferences it trained on.
So what does this all mean for us, for the world? We have small models punching up. We have AI judging AI.
The biggest implication is accessibility. We are entering an era of distillation. You don't need a supercomputer cluster to build a state-of-the-art chat model anymore. You just need a good base model and access to a smarter model to generate your training data.
It really democratizes AI development. It means a university lab or a small startups can build something that competes with the big guys.
It does. But it also raises the issue of synthetic data.
Yeah.
We are moving into a world where small models learn entirely from the outputs of big models. It's a closed loop.
And we should mention the safety aspect here, too. The paper was pretty clear about what they didn't do.
Yes, that is a significant technical detail. The authors explicitly state they didn't filter for safety. Zephyr is aligned to be helpful, but not necessarily harmless.
So if you ask it how to do something illegal,
It might just tell you. Because its training data, specifically the optimization part, was focused on, is this a good, helpful answer? And not, is this safe? The big tech companies spend millions on red teaming to prevent this.
red teaming.
That's where they hire people to attack the model, trying to make it say bad things so they can patch those holes. Zephyr didn't go through that process. This paper proves you can get the intelligence cheaply, but the safety rails are still a separate, hard problem.
So Zephyr is like a brilliant, helpful assistant who just hasn't passed a background check.
That's a fair way to put it. It's a research demonstration, not a commercial product.
Looking forward, where does this go?
Well, the question the researchers pose is, if this works so well for small models, what happens if we apply dDPO to the big ones?
Oh, right. If you take Goliath and teach him these moves.
Exactly. If Llama-3 or GPT-5 uses this more efficient training method, we might see another massive leap in performance. It suggests that our current big models are actually undertrained. They have more potential than we've unlocked.
It's a constant game of leapfrog.
It really is. Zephyr shows that smart training techniques and high-quality feedback can bridge the gap between David and Goliath. It proves you don't always need more muscle. Sometimes you just need better technique.
That's a comforting thought, but I want to leave our listeners with something to chew on. We've talked about how Zephyr learned from GPT-4, the student learned from the teacher, but in this setup, the teacher is an AI, the judge is an AI.
And the student is an AI. We're removing the human from the loop.
Right. So if AI is generating the data to train the next AI, and AI is deciding what counts as a good answer, at what point does the copy start drifting away from what we actually want? If we take humans out of the driver's seat, are we just creating a feedback loop of machines talking to machines?
Slowly evolving into something we no longer recognize.
Something to think about next time you ask a chatbot for a recipe. That's it for this deep dive into Zephyr.
Catch you next time.